So we will model this OA2 beam from the VecTor2 and Sheen 2004 paper, this paper, and these are the cross section, the dimensions of the beam, the properties, all here in this paper. So we will be modeling that using VecTor2. So I fired up Formworks to model this VecTor2 beam. And what I like to start is defining the materials. You can define them here, or you can come to define materials here. So first, let's start with the reinforced concrete, which is the main material that we have. We need first to define the thickness, and the thickness is the out of the plane of the window direction dimension that we need to define. VecTor2 is 2D, so the depth of the members is what this thickness means. So if we go back to our paper, we will see that our OA2 has a B, which is the thickness out of plane of 305. So if we go back and put 305 here, then we need to define the compressive strength of the concrete, which is also here in this paper. You can see an OA2 compressive strength is 25.9. 25.9. Then we have tensile strength, initial elastic modulus, cylinder strain at the F prime of C, Poisson's ratio, thermal expansion coefficient, maximum aggregate size, density, and thermal diffusivity, and then maximum crack spacing. All this you see has this asterisk by the side of the text box. And you can see here that it says enter 0 for VecTor2 default value. So in theory, you don't even need to change this value, you just need the cylinder compressive strength, and VecTor2 will automatically calculate these values that correspond to a concrete of a strength 25.9. If you want to see how it does it in the background, how VecTor2 calculates these properties, you can check the VecTor2 manual. In there they say what are the default procedures to calculate this. So for now we're just gonna leave them as 0 to use the default values, and then we have to input the smeared reinforced properties. So for the smeared reinforced properties, we would smear the stirrups inside the concrete. The longitudinal rebars we will put as discrete truss elements, but the stirrups we will smear in the concrete. In our case, this is a simple case. Our OA2 beam doesn't have any stirrups. You see that all OA series beams doesn't have stirrups, so we don't need to input anything right here. But if we would calculate the percentage, put these two properties here, say what angle it makes with the x-axis, and then click this add button right here. But since we don't have it, let's just update our material so it considers all the values that it's currently here, and then click OK. So now that we created the concrete material, let's create the steel material. So we come to define reinforcement materials, or we could come here to define reinforcement materials. So first, if we go back to our beam, we will need 3 layers for our reinforcement. As you can see here, remember that this dimension, the cross-section dimension in VecTor2 is not going to be modeled because this is the out-of-plane dimension. So we need to somehow bundle these layers into just one rebar layer. So we have 3 layers here. For example, this bottom one will be bundled into just one layer. So the layer will have the aggregate area of these 2 M30 bars. The second layer will only have 1 M30 bar, and then the third layer will have 2 M25 bars. So let's do the first layer first, and if we go back to here, we will see that the M30 has this diameter. So for the cross-sectional area, since we have two M30s, our area would be 1400. So now we will calculate the equivalent diameter that would represent one bar with this respective area. So let's just quickly calculate that. PR squared, so divided by pi square root, so that's r multiplied by 2. That would be 42.2. And now the material properties of the rebar. So if we come here to the M30, the Fy is 436, Fu is 700, elastic modulus 200,000, strain hardening is not given in the paper, but these values are default in VecTor2 and they are most of the times good enough. So let's add it. This will be our reinforcement 1. So our second layer is only one M30, so that's easy. Just copy all the values from here. So let's put one area, the normal diameter, which is 29.9, and then the properties of the material remain the same. We just let's change the color so we can see it later, and then add this new one, and if you click on one you can see the difference. So the third layer would be the two M25s. So going back here, M25 times 2, the area would be 1000. Again, we need to calculate an equivalent diameter for that. Times 2, that would be 35.7. The yield strength is 445. The ultimate strength is 680. And the elastic modulus for this one is different. Now these values are okay again. Color, let's say green. And add. So we have our 3 reinforcement materials here. So now that we have all of our materials, we can start doing our mesh, where we actually create the geometry of the element. So here we have the regions tabs, reinforcement, and then the create mesh. We won't deal with voids and constraints. The regions is where we will create any elements that is not a truss, which is a reinforcement. So you will see how it works here. So to start, we create a new region. This will be our complete concrete beam. So if we look at our OA2 beam, so this would be a OA1, OA2, OA3. So it has a 4570 length. So we can start creating our mesh. So our region would be a 4-point base to create a rectangle, and it needs to be a counterclockwise specification when we create the points here. So let's create the first point at the origin. So we see the point there. And then the second point would be the length of the beam, which is 4570. And you see that it creates the second point and do the links with the line. And then the third point would be just the height of the beam, which is 552 at the same X position, and then 0. And then to close this section, we just click this close button here. And here in the material layers, we can select our concrete, which is our material 1. That's why I like to have the materials created first. Click edit. We don't have any contact elements. For the discretization mesh type, we can leave as it is. This is where we define the size of the elements that we want in our mesh. 100 is good. I'm just gonna put 50 just for the sake of having a finer mesh. Usually we would experiment with this value to see how they impact the actual response of the beam. But for now 50 I think will be fine. Also we would need to pay attention to this value to match the geometry of our element. if we have a mesh that doesn't actually fit in integer numbers inside our region, this could create some different values from this that we input here. So let's add the region now, and we see that when we add it, it creates this one region here. And then now we can start with the reinforcement. This is our beam. Our reinforcement is just the truss. We can start creating the truss. And again, we define now just 2 points will be a line in which the truss will be applied. The line will go from this point to this point, so the full beam. So it's always going to be from 0 to the 4570, which is the full length of the beam. But the height of this line is what will change from each layer that we have. So our first layer is at 64 from the top, from the bottom, sorry. So this will start from 0 and 64, and it will go all the way to 4570 on the other side. The truss material will be our reinforcement 1, and we can add the truss, and we can do the same for the other ones. So this would be 64 plus 32, 96, and 4570. That will be reinforcement 2, add the truss. This would be 128, 4570, and reinforcement 3, add the truss. So now that we have our beam and our reinforcements created, we can click to create our mesh. So in here we can simply click this button, create the mesh. It's good to save first, because sometimes the program crashes if you can't create a mesh. So it's good to have it saved before. So we can, just gonna save as VOA1, formworks, save, and now I hit create mesh. And you can see it creates the elements and all the beams, all the reinforcements, and you can see it uses the colors that we specify for each reinforcement material that we created. Even though we can see it right now, the mesh doesn't actually exist. If we close this window, everything you see will disappear, because we have to add the mesh to a structure so the elements can be actually created. So when we click that, you see that a lot of numbers shows up. Each of these numbers are a element number, so we can come to this display options and remove that, because they just let's also remove node numbers because they stay in the way, and then everything gets cleaned up again. So now we have our concrete beam, our reinforcement, and that's it. In theory, we could simply put our boundary conditions, which are our load and our supports, and we were good to go. The problem is that right now we only have concrete, and if we apply a load or a support directly to one of these nodes, this could create very high stresses in our concrete, and it would cause it to fail earlier, which is not what we want. It's not realistic. So for that, we will want to also include in the model this steel supports that the load applies into, and also the supports. So the actual plates that were used in this experiment is listed right here, and we can see it's a 150 wide plate and 20 millimeters thickness. So we want to include that also in our model. So for that, first let's create the steel material in which this plate will have. In here I'm going to create this as a structural steel. The thickness will be the same as our beam, which is 305. The yield strength will be 400 MPa. These are just general steel properties, and you can see that I'm basically copying from the reinforcement steel that we have. those are commonly used values for structural steel. So I'm just gonna add it. That's all we need: the initial stiffness, yield strength, and ultimate strength. I'm gonna add this. So remember, our steel is material 2. Let's also change the color so we can differentiate them. Let's make it a light gray. Update. Okay. So I'm just gonna save it again, and now we need to include that in our model here. For that, we will also create regions. The problem is we already have one region and one mesh already created in the structure. So if we create another region right now and include it in this mesh, the regions won't be connected. These nodes won't know that will be something here that will be our plate. So it is better to delete the structure and clear the mesh, and then include the new regions that we will input, and then mesh it again. I just meshed the beam first, just so you know, in an easier way how it works. Now let's include our new region. So let's go back here. So remember that our beam in the VecTor2 starts in the middle of the plate, from the middle of this plate. That's where our length in here is considered. So our model will only have half of the plate. So if the plate is, remember, 150, our plate here will start from here and we'll only have 75. So let's create a new region. That will be our new plate. The first point will be 0, so the same point as this one. And then counterclockwise, we go down the thickness of the plate, which is 20. So let's go minus 20. And you see that over there. And now the length of the plate, which will be 75. Go back the thickness, close the region, include our material 2, and in here, remember, we have 75. So 100 would not be enough for this, but 25 would. So we can put set 25, and that would have 3 elements in the plate region. So let's add this region. Also, let's do the same for the other side. So create new region. The length is 4.70. And now we will do the plate where the load will be applied. So if we go back here again to this image, this plate is identical, so it's 150, but we are now modeling the full plate. So that will be the exact 150, and also the thickness has changed to 58. So go back here. This will be in the middle here. So the X position would be the length of the beam, 4,570 divided by 2, and then half of the plate, minus 150 divided by 2, which is 75. That gives us, let's create this region, a X position of 2,210, and the Y position will be the height of the beam, which is 552. Where is that? 552. So if we click here, we should see this point, and then the second point would be this plus the length of the plate, 2,360, and then this plus the thickness of the plate, which is 58. We can use 58 is actually good because when added to 552 will give us a round number of 610. and go back to the original one, which I don't remember, but I can always come here and see all the points that were created. So 2, 2, 10, and then close. I'll also use material 2. And for this one, I have a 150, so 50 would be good. And for the Y dimension, it is actually 58. So using 50, that would use only one element. Let's just use 25. So 58 is not exactly divided by 25, but with this maximum aspect ratio, VecTor2 formworks will adjust the mesh to include, I believe, 2 elements. Let's see. Let's add the region, create the mesh. Before we do it, let's save it just to prevent, and then create the mesh. So here we can see that formworks has adjusted the mesh in these regions because we put different values for the elements here. So to have this continuity between the plate and the beam, it adjusted the mesh both in the sides and here in the middle here. So the window vanished, but I believe it's still here. Okay. So right now I click add to structure, add mesh to structure. And since I removed the numbers, it doesn't show the number. If I close this now, it's still here, which is good. So now we can add the boundary conditions and load to this beam. So the loads, first we need to create here in the job, define job. You can see here on the top. You can also come to job, define job. So click here and activate at least one case. Those are load cases, so we need at least one to be able to input actual loads to our beam. But before we do that, let's do the boundary conditions. So support restraints. In here we see that we have 2 rollers in the actual experiment. If we put 2 rollers in the finite element, it will create an instability problem. So we can create a simply supported condition. So here in the create support restraint, I can manually type the node number. I can specify which restraint I want and the increment, or I can select the nodes by either the pointer, you see what it does, or the window, which select multiples. So I can create the pointer, and I'm gonna select this node here, and this node will be selected to enable this plate and the beam to rotate. And this will simulate this roller condition here. You can see it's like a point load in the plate. So for this one, I will restrain both X and Y to create a pin, and then I'll do the same thing on the other side, with the exception that I want only Y in this one. So this is a simply supported condition. Done. And for the load now, what I usually do is that, for example, I'm looking at OA2, which the response is about this. So I see that the response goes to about 17 millimeters. So I usually come at apply displacement, apply support displacement. Again, I will select the node here. I try to pick the center one, which is exactly this one. If there isn't one at exactly the center, you can select the 2 that are closest to the center, or yeah, the 2 to create asymmetry condition instead of slightly eccentricity from the center. In any case, the load will be Y direction, and it will go down by, let's say, 17 millimeters. So that's it. All our model is now created here. Now we just need to define a little bit more things here in the job, and then we'll be good to run. So in here, I can give it a name to this load file, a title in case I want to specify the name so I remember later on. Here is what I defined the load type: monotonic, cyclic, and reverse cyclic. Our case would be monotonic. and then the initial factor, the final factor, and the incremental factor. Right now it's all 0, so if you would run this now, nothing would happen. So our initial factor is how much of this load it will be applied at the first interaction. So I want it to be 0, the first interaction, then will be nothing. That's good just so the model, make sure that everything is in place, all the stiffness matrix doesn't have any weird mistakes. The final factor, I want to be the full displacement that I apply, and I go, this can be anything you want, but I like to go at least 10% at a time. So we'll start at 0 load, and then you will apply 10% of 17, which is 1.7, and then another 1.7, which is 10%, 2.4, until it reaches 17. If that doesn't converge, we can also go back at 5%, 1%, you can choose that based on how you feel necessary. For now, we don't need to change anything in this region, we just need to click OK. And now we save all of the files here before we run the analysis. First the job, then the structure, the loads, and once that's done, we can simply run the VecTor2 processor. I won't run it now, but when you click here, the analysis will actually occur. And when it's done, we can use either Augustus or Janus to visualize the results. So that's it. This is how you model a reinforced concrete beam in VecTor2.